Hi. In this module, we are going to see some aspects of sample size, how much subjects you require to do a study, and some of the concepts that goes behind the calculation of sample size. The usual question most of the investigators they have in their mind when they want to start doing a research study is, how much subjects that I should recruit into my study, how many patients I should see, how many households that I should cover. And a simple answer for this question is, there is no simple answer. Yeah, this requires a little bit of logical thinking and usually it depends on some of the information that we already should know before we start our study. So in this module, we will try to understand what's the relationship between sample size, and I'm going to introduce you to a concept called power. And we also try to determine the sample size, which is absolutely essential or necessary to achieve a given level of power for estimating maybe a simple proportion or any other measures of effect. As I was mentioning to you, there is no simple answer for estimating a sample size. We need to go in a systematic manner, and let me take you step by step in the process of estimating sample size. First of all, you'll have to identify what is the major study variable you are planning to study. In any investigation, you will be seeing a number of things. You'll have to identify which among them is the most important variable which you want to study about. Say for example, when you are studying on maybe scrub typhus in a community, your aim may be to estimate the prevalence of scrub typhus, in which case the variable whether a person has got scrub typhus or not is a major variable. Suppose if your interest is not on the prevalence but on some of the associated factors, whether a person has been exposed to a forest or something like that, in that case that becomes the major study variable. Then the second step is to determine the type of estimate. Are you going to study a mean or a ratio or a percentage or proportion? And because accordingly we need to reframe or have a formula for computing the sample size. Then one of the important things that comes out is you need to indicate the expected frequency of factor of interest. Say a common sense says, suppose if you are going to study something very rare, you need to have a large sample. Unless you see a very large number of people, you may not probably get sufficient number of people with the factor of your interest. On the other hand, if you are going to study something which is very common, in that case you don't need a large sample. Even in a small sample, you may be able to give fairly a good, sufficient and precise estimate of your factor of interest. Then the next factor is the desired precision of the estimate. How precise you want your estimate to be. You want your estimate to be within 5% this side, that side, or within 10% this side, that side. See, as you want your estimate to be more precise, then naturally you need to have a larger sample. If you are willing to give, say, plus or minus 20%, then probably your sample size will be small as compared to plus or minus 10%. Then the next point is, okay, I want plus or minus 10%, but how sure I want that my estimate is plus or minus 10%. What is the amount of rather risk that I am willing to accept, either a 5% risk or a 10% risk? So, these are all some of the elements that are essential to compute the sample size, and invariably these are all the elements that has to be rather given by the investigator to whoever is computing the sample size. The other three items that I have rather given are, you have to adjust for population size. Are you going to take your sample from a very large population, or you are going to rather take from a small population? Because usually the sample size formulae assume that you are taking sample from a very large population. If you are going to rather take your sample from a small population, you need to do some adjustment factor into it. The next is adjust for estimated design effect. You see, in my earlier lecture on sampling, I talked to you about a cluster design effect, wherein you are going to rather select not individual subjects as your sample, but you are going to rather select cluster of subjects as your sample. There could be a correlation between the subjects in the same cluster. So, in order to get over it, you need to multiply your sample size by a factor called a design effect, so that you have a larger sample which takes care of this correlation within the subjects in a cluster. Then the last bullet point in this is adjust for expected response. You have to rather, you decide that you want to rather do 300, and if you just go and study 300, maybe 10% of them they did not turn up, and you have only 230. So, in order to adjust for that, you have some maybe 10% extra as your sample size, so that assuming a non-response, you still have sufficient sample to answer your question. I am going to introduce you now to some concepts which are essential to understand the computation of sample size. The first one is the alpha, or the type 1 error, the significance level of a test. What do you mean by that? It is the probability of rejecting the null hypothesis when actually it is true. In the statistical parlance, it is called type 1 error, and the confidence level is the complement of that is 1 minus alpha, and that is naturally the probability that an estimate of a population parameter is within certain specified limits of the true value. The next are beta and power. Beta is nothing but the probability of failing to reject the null hypothesis when actually it is false. So, if something is false, you have to reject it, but you accept it. And the probability of making this is called a type 2 error, and the complement of this, that is 1 minus beta, is commonly denoted as power, and which is a correct decision, and that is nothing but probability of correctly rejecting the null hypothesis when it is false. Another important concept that goes into the computation of sample size is the precision. By precision, what you mean is it is a measure of how close an estimate is to the true value of a population parameter. It may be expressed in absolute terms or relative to the estimate. They say plus or minus 10% or plus or minus 10% of the estimate. Now, let us rather look into a scenario where you need to compute a sample size and your interest is to estimate the mean of a population. So, you have a sample, you have to compute a sample mean, and you want to estimate the population mean from your sample mean. And what should be the sample size that you need? So, the general idea of the computation of sample size is, it's a reliability coefficient into standard error is called D, and through D we can estimate the sample size n. Say the D is a formula given here is Z into sigma by square root of n. How do we get that? We get that mainly using the concept of a sampling distribution. What do you mean by sampling distribution? Suppose I take several samples of the same size, and each of the sample give an estimate of the population mean, and if I have a distribution of all those sample means, theoretically it is proved that that distribution is a normal distribution, and also the standard error, which is the standard deviation of that distribution, is given by sigma by root n. So what we normally do it is we try to rather have using the principles of normal distribution, 2 sigma limit of the sampling error, 95% of the values they lie. So the Z in the formulae is nothing but the standard normal deviate for a particular level of significance. And suppose the idea of sample size is you fix that, and then when you fix that you have only one unknown, namely the n in the denominator, and if you can solve for the n, which is nothing but n is equal to Z squared into sigma squared by d squared, then you get an idea of what the n is. I think these concepts will get clearer if you see an example. A health department nutritionist, he wishes to do a survey among a population of teenage girls to determine the average daily protein intake. So that's the research problem. And what information is needed to estimate the sample size? So the nutritionist must provide 3 items of information. The first one, the desired width of the confidence interval. The next one is the level of confidence desired, and he should rather give a rough magnitude of the population variance. Assume that he gives them all. Say the nutrition feels that okay, the 10 units this side and that side is what he is expecting, which means 10 units on the whole, so 5 units this side and 5 units that side. And the confidence coefficient of 95% is decided upon, and from his past experience, from the literature review, the nutritionists feel that the population standard deviation is probably about 20 grams. So now we have the information Z is 1.96 because 95% confidence interval has got a corresponding Z value of a normal distribution 1.96. Sigma is already given as 20, and then the desired length D is 5 units this side or that side. If you plug in all these values into the formulae, it becomes n is equal to 1.96 square, 20 square, multiply these two, divided by 5 square, it comes to 61.47, which means you need to have at least 62 teenage girls in order to get an estimate of the mean protein intake, and the estimate that you give 95% of the time will be within 5 units this side or that side of the true mean population mean of protein intake. Now in this formulae we have sigma, that is the population variance, and in most scenarios you may not probably know a value of sigma, because this is a study you are going to rather do, sigma may not be available. And how to get a sigma? One of the way that you can get this variances is do a pilot survey, preliminary survey, and of course you can even use this observation used in the pilot for your final sample too, and an estimate available from the pilot survey could be used, or you can use an estimate which is available from previous studies. And suppose you have a large data available and you have the range of the data, assuming that it's normally distributed, you can get an approximate value of sigma as the range divided by 6. So, these are all ways of getting the value of sigma in your formulae. Now, suppose we are going to estimate a proportion, not a mean. The formula is more or less similar, but what you need to rather give is you must rather have a knowledge of P, that is the proportion of the characteristic or the factor of interest in the population. This also may not be. See, you are going to do a study to estimate the proportion, and invariably when I ask this question to the investigator, he says, sir, I am going to rather do a study to find it, how can I have an idea of P? Can probably, as I had rather mentioned earlier, can probably do a pilot study to get an idea of P, or you can get from the literature what could be the value of P. And if it is impossible, then the best thing is to estimate to get a value of P as 0.5 so that it is the maximum value of N. So, the formula for that is very simple. The N is the Z squared and the D squared in the denominator are common, and here instead of your sigma what you have is this the PQ, where Q is nothing but 1 minus P. This also will be clearer if we see an example. Suppose want to estimate the true immunization coverage in a community of school children. Previous studies tell us that the immunization coverage should be somewhere around 80%. Suppose the precision, the absolute precision, we would like the result to be within 4% of the true values. Then the confidence interval, which is conventionally taken as 95% and 1 minus alpha, therefore, the 5% alpha level, the Z alpha is 1.96. Then we have all the values that are needed for our calculation. D, the absolute precision is 0.04. P, the expected proportion of population is 0.8. So, naturally the Q must be 0.2. Then Z alpha is 1.96, and when we plug them all into a formula, what we get is 384. So, you need 384 subjects to get an estimate of the immunization coverage within 4% this side or that side, and you have 95% confidence that the true value lies in this particular interval. So, we had seen something about I talked about the design effect earlier. The design effect is caused because of a bias in the variance introduced in the sampling design by selecting subjects whose results are not independent from each other, because in a cluster there may be, suppose a child is immunized in the first household, there is a fairly large chance that this child in the next house also is immunized. You can't say that it would be absolutely independent. So, in order to account for that, you need to multiply your sample size by a factor called design effect. Then, suppose in a similar sort of a scenario, suppose we are going to rather do a case control study or a cohort study, and how you should go about in estimating the sample size. So, what you need is the desired value of the probabilities of alpha and beta, and the proportion of baseline, or that is the control or non-exposed population, and in the case of case control studies, the proportion of exposed, or in the case of cohort studies, the proportion of disease. And you need to rather have some idea of them, and these are all often based on previous studies or reports, and also you should have some sort of an idea of the magnitude of the expected effect, that is the magnitude of relative risk or the odds ratio. This again is based on previous studies or reports, and what's the minimum effect that investigator considers worth detecting. See, these are all some of the information once it's provided. Then there are very easy formulae available, the different formulae depending on the study design, research question and the type of data. Now, let us rather take few examples and this example should rather give you some idea of how the sample size is computed in different scenarios. Take for example a cohort study of oral contraceptives used in relation to the risk of myocardial infarction among women of childbearing age. So previous studies have indicated that the proportion of non-OC users who are at risk of disease is 0.15. That is 15% of non-OC users, women of childbearing age, have a risk of myocardial infarction. So proportion of OC users who are at risk of disease is 0.25. And so the conventional alpha is 0.05, and suppose the beta is taken as 0.20, that is you want 80% power to detect the difference of if it truly exists, and assume that you are going to rather have equal sample sizes for your users and non-users, then the formula is obtained using this following parameters. You know P naught, which is nothing but proportion of non-OC users who are diseased, which is given as 0.15. P1 is proportion of OC users who are diseased, which is given as 0.25, and your Q naught, which is a complement of P naught, is 0.85. Your Q1 is a complement of P1, which is 0.75. Z alpha is 1.96, we saw in the last example. Z beta is 0.84. So we have all these values which can be plugged into the formula, which gives n is equal to 246.96 or 247. So we need to have 247 OC users and 247 non-OC users, follow them over a period to get a desired result. Now let us rather take an example of a case controlled design. How do you go about? In a case controlled study of oral contraceptives used in relation to the risk of myocardial infarction among women of childbearing age, previous studies says 10% of women use OCs, and OR of MI associated with current OC use is 1.08. Then the other thing as conventional alpha is 0.05, conventional beta is 0.20, and assuming equal size for case and control. And so you have all these parameters. P naught is equal to the proportion of controls who are current OC users, which is 0.1. P1 is equal to proportion of cases who are current OC users, and that is 0.18. Q naught is 0.9 and Q1 is 0.82. Z alpha 1.96, Z beta is 0.84. If you plug them all in a formula, then you get 291.06, in which case it indicates that you need to either have 291 or 292 cases and 292 controls in order to get an estimate of your OR. Now this slide gives you the required sample size for various OR. Say for example, you want to detect an OR of 1.2, then you need a sample size of 3,834, whereas you have to estimate an OR of 3, it is enough you have 59 in each group. So what it means is if you want to detect a very small difference, then you need to have a large sample to identify that small difference. If you want to detect a large difference, then it is enough you have a small sample, then you will be able to get an estimate of your OR, which is 3 or more. Then see, in any of these analytical studies, when you are looking for an association of one variable, there could be a third factor which could be affecting the values of this association, which is in the epidemiological parlance we call that as confounders. There could be one variable or two variables which are confounders in a particular association. So the general rule is, if you have some confounders in your studies, you hike your sample size by 10% for every confounder variable that you have. And now, having seen different scenarios where the sample size is computed and then the concepts behind it, I am going to introduce you to two softwares which are free softwares in the open source, which can be very easily used to compute sample size of different study designs. One is called OpenAP, and this software is supported by the CDC Atlanta, and the website for that is www.openap.com, and it's a very simple software to use. There is a tutorial for this particular software which gives you some examples, and depending on what sort of a study design that you have, you can plug in the values that the software asks and you will get the desired sample size. Another one which is called PS, that is Power and Sample Size Calculation. This is by the Department of Biostatistics, Vanderbilt University. This is also an open source software. This is also fairly user friendly software where you can rather compute your sample sizes. So whenever you do an investigation and when you compute the software, you give this software in your reference saying that you use this particular software, and these are all the assumptions or these are all the values that you had rather plugged in this software, so that this is my sample size. This should be reflected in your method section. So to recapitulate the module, sample size, there is no magic number as a sample size available. Sample size have to be computed using various parameters that are supplied by the investigator. Investigator may have some idea of it ready-made. If he doesn't rather have those ideas, he may have to probably do a pilot study to get this out of an idea. And then it depends on how much risk that you are willing to rather take, how much precision that you want on your estimates. And this is usually, there is no fixed number. We can always negotiate depending on the resources that are available in terms of money and time. And suppose I say you need to rather have 300 and you don't have that much resource and you don't have that much time to rather do, you can always rather reduce the sample size, but you should know what price that you are going to rather pay for reducing. You may have to rather compromise on the precision or the risk that you will be rather taking on these sort of estimates. Thank you so much.